Okay, I'm going to be doing a couple of videos on completing the square. When I teach completing the square in the classroom, I uh, typically start off with easy examples, and we ramp our way up to more difficult examples. And I kind of jokingly refer to it as leveling up. So when you're just beginning, we're on level one. So showing my video game nerdness there. But anyway, in this video, we're going to do an introduction to what we mean by completing the square and set up the basic idea, and then do a couple of examples with at the level one, the easy level. So we're going to start off by looking at a perfect square, and so and specifically a perfect squared binomial. So x is our variable, and then b, and I'm going to use a capital B for a reason. So capital B is a constant. It's a number of some kind. Could be positive, could be negative. And we square that. So if this is what we're working with, then to square it, we're supposed to take x plus capital B and multiply it by itself. To multiply this requires FOIL. And so when we FOIL it out, firsts, outers, inners, and lasts. So last would be b times b is b squared. The two middle terms are like terms. They're both a number times x to the first power. So we can write this as x squared plus, we have two of them, so 2b times x plus b squared. Right, so now I did not specify what b is. So this could be any x plus a number, even x plus a negative number. Sorry, so this could be x plus 4, or x minus 3, or x plus 0.5, anything. But when we multiply it all out, it will always have this pattern. The first term will be x squared. The middle term will be 2 times whatever b is. So that'll be a number times x. And then the last number will be b squared, whatever b was multiplied by itself. So it turns out that any quadratic has this perfect square lurking somewhere inside it. So completing the square is a way of adjusting the way a quadratic looks so that we can find this perfect square. And to do that, we'll take the quadratic and we'll match it up to this pattern. So this is the pattern we're going to use, because if we can get this pattern right here, it will automatically, without any effort on our part, factor into x plus b times x plus b, and that is just x plus b quantity squared, the perfect square. So we're going to be using this pattern down here. Let's do a quick example. Like I mentioned, this is level 1. So we're going to complete the square on x squared. And usually when I do this in class, I have students pick numbers randomly so that they know I'm not rigging this up. So, but you'll have to put up with me rigging it up for right now. Okay, so x squared plus 12x minus 17. Now, what we want to do is we want to match this against the pattern. So the pattern is x squared plus 2 times b times x plus b squared. So if we go term by term, starting with the x squareds, the term we're working with is 1x squared. Does that match the pattern? Yes. So we're good. What about the second term? Well, the second term, we have a 12x, and what we need is a 2 times b times x. Well, that's okay. That matches as long as we make a relationship, we state a relationship between 2b and 12. In order for this to match, it must be the case that 2 times b from the pattern has to be the same as the 12 that we have. So we define it this way. 2 times b is going to be equal to 12. And that means these two terms match. The last term becomes problematic though, because b squared depends upon what the value of b. Well, we know that 2 times b is equal to 12. So if we divide both sides here by 2, we see that b is equal to 12 divided by 2 is 6. And b squared then is 6 squared, that's 36. Our constant term, in order to match this pattern, our constant term needs to be 36. What we have is 17. So we're going to have to change the way our constant term looks. We can do that. A standard technique that mathematicians use is they can add a 0. Now, if I add a 0, does that change the value of what we have? Of course not. Adding 0 doesn't change anything. But we are clever. We know that there are lots of different ways to write a 0. And we're going to write the 0 as plus the number we want. And the number we wanted was 36. And minus 36. Since 36 minus 36 is 0, this is still just saying plus 0. We haven't changed the value. We've changed the way things look, but we have not changed their value. Now, luckily, addition is what we call associative. That means we can, as long as we're careful with our signs, we can adjust the parentheses. So we can drop the parentheses here. And again, the positive 36 and the negative 36, that's a 0. So it will, if we wanted to, we could go back up this direction and it doesn't change the original statement. But again, using associativity, we can choose to group things the way we want to. And so what we're going to do is we're going to group the first 3 terms. Now look at these first 3 terms. X squared, 12x is the same as 2b times x, because that's how we defined it originally. And that told us b was equal to 6. And here we have b squared. 6 squared is 36. So these first 3 terms are a perfect square. Since they're a perfect square, moving back up to the top, anything that is in the perfect square pattern, we could split the middle term up factoring by grouping would give us x plus b times x plus b, and that would be x plus b squared. But we don't need to go through all that work because we already know the value of b. We found it. B is equal to 6. So since these three terms are a perfect square, these three terms will automatically, immediately, without any effort on our part, factor into x plus b, capital B, which is 6, squared. And the two constant terms on the outside, we just combine those together. So negative 36 minus 17 is negative, what, 53? Hope I did that in my head correctly. And this is the completed square form. In general, completing the square is a method for taking a quadratic in its trinomial form, where a times x squared plus bx plus c, a, b, and c are numbers, and transforming it, rewriting it into its completed square form, which will look like this. So this, by the way, is the reason I used a capital B. I didn't want it to be confused with the lowercase b, which is how we typically write the trinomial form. And k is just a constant. All right, let's do another example. All right, so here we go. All right. In order for this to work, we have to match this up to the pattern, which is x squared plus 2 times b times x plus b squared. There's our pattern. So we start at the beginning. Do the x squared terms match? Yes, they're both 1x squared. Move on to the linear term. Do the linear terms match? And the answer is yes, the linear terms match if we associate or define 2b to be equal to the coefficient. Now, like we did in the factoring videos, we have to be careful with the signs. The coefficient on x is not 22, it's negative 22. So as long as we state 2b is equal to negative 22, then we will match on the middle terms. So let's do that. I'm going to move over to the side here, and we're going to define 2 times b for this problem is negative 22. So now we match on the quadratic terms, and we have defined 2b in such a way that we match on the linear terms. But now we get to the constant, and the value of the constant depends upon b. And b has already been defined. 2b is negative 22. Therefore, if we divide both sides by 2, we see that b is equal to a negative 11. Okay, in that case, b squared is negative 11 squared, which is 121. So we need this to be 121 in order for us to match. Well, we're going to have to adjust our constant. In the previous example, I showed you how to add 0, and that will always work. Sometimes the numbers are simple enough that you can tweak the constant a little bit more quickly, and that's what I'm going to do here. So I'm going to write this. I'm still going to add 0. X squared minus 22x. Here's my plus 100. Now what I really need is this to be a 121. So how much am I lacking? I need this to be 21 bigger. So I'm going to add 21, and to compensate for adding 21, I will subtract 21. 21 minus 21, that's a 0. So I haven't changed the value. But since addition is associative, I can drop the parentheses, and then I can combine these two terms. Now notice if you take 121 minus 21, that's equal to 100, which is what we started with. So this still has the same value. It just looks different. But now, if we check the first 3 terms, we look at just the first 3 terms, x squared, 2b times x, and this is 2b times x because that's how we defined 2b. And since we know b is equal to negative 11, the constant term is b squared. We match b squared. We match all 3 terms. So the first 3 terms are a perfect square. Perfect square. And we have this minus 21 hanging out on the outside. But because this is a perfect square, we know that this will automatically factor into, going back to the pattern, right? The perfect square automatically factors into x plus b quantity squared. All right, so x plus b. So these first 3 terms will factor into x plus b. What is b? B is negative 11. So plus a negative 11. It's the same as minus 11. So x plus b squared. And then we have this constant term that's hanging out at the end. This is the completed square form. All right. Now, let's say we wanted to check, make sure our work was correct. We can do that by FOILing out this term. So let's check it. So x minus 11 squared would be x minus 11 times x minus 11. And we'll have to subtract 21. Using FOIL, x times x is x squared. X times negative 11, that's the outers. X times negative 11, that's the inners. And negative 11 times negative 11, negative times negative is positive. 11 times 11 is 121. So that's the FOIL part, and then we still have the minus 21 here at the end. These two terms are like terms. So x squared, negative 11 minus 11, that's a negative 22. And 121 minus 21 is 100. And that is the original. Why didn't you guys tell me it was off the screen? You guys are too quiet on these videos. My apologies. We're looking at my paper. All right, sorry. Okay, now that you can see it, let's go back. All right, so here's where I took the x minus 11 and I wrote it side by side to FOIL it out. The minus 21 that we had on the outside here is still right here. So when we FOIL it, we get the x squared for the outers minus 11x, sorry, x squared is the first, negative 11x is your outers, x times negative 11. The inners give you negative 11x again, the inners x and a negative times a negative 11. And then the last, negative 11 times negative 11, negative times negative is positive, 11 times 11 is 121. These two terms combine, negative 11x gives you twice as negative 22x. And then 121 minus 21 is 100. And so this is exactly what we had before. So it works. Now, the reason I wanted to show that this check to you is for this reason. If you need practice with completing the square, it is very simple to do. These were level 1 examples. At level 1, what you're going to do is you can just pick values, right, for A, B, and C. But for level 1, keep A equal to 1. And pick B so that it is even. C can be anything you want. So if you want to practice this, just literally pick an even number. Positive or negative, doesn't matter. In fact, you should do both. I used a negative 22 on this last example. Just pick an even number, anyone you want, and write it down. So like, I don't know, -8, -6, right? X squared minus 6x. The A value is 1. The little b value is even. And then C, pick any number you want. I don't know, 73. It doesn't matter. But here's a perfectly good level 1 trinomial that you can practice completing the square with. And so as long as you're willing to pick an even number for your middle term, you can create your own practice examples and then check them by FOILing out and build your skills that way. All right, I'm going to have a couple more videos on completing the square. I'll have them up as soon as I can.